Welcome to the video on finding volumes by cross-section. Down here we have two examples of what a volume by cross-section could look like, and we're going to see a applet that shows us how these are built in just a moment. First off, I want you to understand that what we're doing is actually nothing new if you already know disk and washer method. So I have a picture where we've got disk right here and we've got washer over here, and we've really been doing volumes by cross-section because here in disk our cross-section has been a circle with a thickness which is delta x, right? So when we did this integral, we would say, okay, well each cross-section was pi r squared times delta x. So we had pi, and we knew this thing went all the way from -3 to 3. Our radius is the distance from here up to this function, which we called f of x. So we've got f of x squared, and then dx is our thickness, because our thickness goes across. Likewise, for washer, we knew that we were working with something with a little radius and a big radius. So we knew that our cross-section was going to be pi, a big R squared minus a small r squared. And again, our thickness is delta x. And so that's the volume. And so when we write our integral, we've got pi, the integral. In this case, it goes all the way from 0 to 2. And our big radius goes up to this top function, g of x. So we have g of x squared minus our small, a little radius, which goes to this function, h of x squared. And delta x is becomes dx as it's heading to 0. So all along we had these cross sections. So now let me show you what it looks like with different kinds of cross sections in this applet. So here I have an example where our cross sections are squares, and we can see all the different squares that can fit along this base, and I can generate the entire solid. Maybe it's not always just squares. Maybe I want semicircles. And let's just go back to state where we see there's our cross section, semicircles, and there's all of them. Or I could have, I've got so many choices, I could have rectangles. And there's all of my rectangles, and we can see that sample rectangle across there. Now this one, my base was this triangle, but if my base is a circle? So now here I've got those squares, I have all those different squares back and forth, and I can generate the entire solid. That was the picture on the front page. Or maybe I want equilateral triangles, and there's all of my cross sections, and I can generate that entire solid. That was the other picture on the front page. All right, so let's try and do these types of problems. And here we go. We've got the picture we were just looking at with squares on the base of our triangle. Now we're going to always call, in this video, the cross-section height as S. And in this case, you can see its thickness is delta x. And from what we've learned before, we know that height S is going to be the top function minus the bottom function. So S is going to equal -1 plus x over 2 minus 1 minus x over 2. And let's just simplify that so it's a little easier to work with. -1 plus x over 2 minus 1 plus x over 2. And that's going to simplify to -2 plus x, because I've got half of x here, half of x here. Together it's 1x. Now we need a formula to work with this, and we see that we've got a square here. So this square, we said the bottom is called S. That means its height's also going to be S. And we already said its thickness was delta x. So 1 square is going to be S squared delta x. But I want all of the squares. So when I want all of the squares, I've got my integral. I start here at 0, end at 2. So from 0 to 2. And my S, that S squared, is going to be that value, -2 plus x. I squared dx, and I have written an integral that finds the volume of this figure right here. All right, now we can see how we just used that formula, and we're going to create formulas for all 4 of these cases. So for the square, and because sometimes it's delta x and sometimes it's delta y, we're going to let the thickness be represented by t on this page. So right here, I'm going to use delta t to represent the thickness right there. And so when we're working with a square, we just saw this one, we're going to have the integral of s squared dt. That's supposed to be an integral. There we go. All right, let's go down to the rectangle because it's pretty easy. Again, we have delta t, and remember our rectangle is just base times height. In this case, we're calling our base s. So our formula is going to be the integral of s times h dt. Now our equilateral triangle, we got to remember some geometry to do that. So I'm going to go to a clean slide here, and you'll recall that in an equilateral triangle, not only is every side equal, every angle is equal. And then you might also recall that if I draw in this altitude, I'm going to split it in half, and I end up with 30, 60, 90 triangles. And hopefully you remember that the ratio of the sides of a 30, 60, 90 triangle is 1 to 2 to root 3. And so if this side, let's see, let's go back to, I guess, green. If this whole side is s, this little side is 1/2 s. And to find this side, which is our height, we multiply 1/2 s times root 3. So our height is root 3 over 2s. And all this is needed because I want to know the area of this. Area of a triangle is 1/2 base times height. 1/2, my base is s. My height is root 3 over 2s. And when we simplify that, we get that the area is root 3 over 4s squared. Now we did all this work so you don't have to do all this work every time you do one of these problems. You can simply memorize this formula. Now in addition to that, we're going to add a thickness. So our thickness again is going to be delta t. And so our formula when we're integrating a series of equilateral triangles is root 3 over 4 outside, it's our constant, the integral of s squared dt. Let's do one last one, our semicircle. Our semicircle is going to have an area of 1/2 pi r squared because it's half a circle. S is this entire distance across here, which means our radius is 1/2 of s. So we've got 1/2 pi, 1/2 of s squared. When we square that, we get 1/4 s squared. And when we multiply that all out, we get pi over 8 s squared. And that formula will also save us time when we do these ones. Again, our thickness is delta t, so our integral is going to have the constant pi over 8 out front, and then it's going to be s squared dt. I want to just take a minute to note, when do we have pi? Remember these, we had pi because our cross sections all involved circles, so you're going to have pi. Now with squares, no pi. With triangles, no pi. With rectangles, no pi. Semicircles, we've got pi in our formula again. So if it's circular, there's pi. If it isn't, no pi. All right, so let's go and do this other picture that we saw before. And in this one, we have cross sections that are equilateral triangles. And we will have memorized this formula, root 3 over 4, the integral of s squared and delta, and in this case we can see our thickness goes across, so delta x. So if we fill this out, root 3 over 4, the integral is going to go from -2 to 2, so that's good. And we still need to figure out what is s. We squared, it's going to be dx. So let's figure out what is s. It's going to help to take this formula and solve it for y. So y equals the square root of 4 minus x squared. Bear in mind that that's the positive root, so it's just the top half. But if I know the top half here, I can simply double it because I know I have the same amount on the bottom. So 2 square root 4 minus x squared is the length of s. And we've got our integral. Let's try 2 more problems. This time we have a completely different region, and we are told that the region we see is the base, and cross sections perpendicular to the x-axis are semicircles. So let's draw in a sample rectangle. So here's my sample rectangle. I know it has to be perpendicular to the x-axis, and that gives me a width of delta x. I know it's semicircles, so it's going to be pi over 8, an integral of s squared dx. And I know that everything's in terms of x, so it's going to start here from an x value of 0 all the way out here to 9. So I've got pi over 8, the integral from 0 to 9, and s is this height, which is root x. So I have root x squared dx, and we're done with this problem. All right, one last problem. What is different in this one? We're finding the volume of a figure whose base is shown below and cross-sections perpendicular to the y-axis. So this time we're perpendicular to the y-axis, and they are rectangles with a height of y. So let's draw in our cross-section. First off, we have to be perpendicular to the y-axis, which means this is going to be delta y. And we see that the height is related to y, which means like this rectangle right here would have a height of 1. But as I headed up here, I'd have a height of 3, and here my height is 2.5, and so forth. So wherever my y coordinate is, that determines the height of my rectangle. So we know that for a rectangle, we're going to have our side times our height, and in this case, it's delta y. We can see that these are going to be stacked up using y values from 0 up to 3. So here we go, integral from 0 to 3. And we need to figure out the side s. To figure out the side s, this is one of those right minus left situations. So our right function is 9, and our left, we have to solve for y, which means x equals y squared. So it's going to be 9 minus y squared. And then we have to take that times the height, which is y, and then we've got dy. And we have completed this last problem. All right, good luck on your homework.